Awesome, cool. Thank you very much for having me today from home office. So we're going to spend the next 4-ish minutes, I hope I don't go over time, talking about how we can build better and safer batteries using the insights we can obtain from thermal runaway calorimetry. Like you said, Max, it's really, really good to prevent thermal runaway no matter what the application is. So we're going to have a quick look at thermal runaway in general. What is it? How can we describe it? We're going to look at why exactly it makes sense to prevent it, even when there's not a clear certification requirement that forces us to do that. We're going to look at our DATRC method, what type of data we can obtain from that, and example data. And then we're going to look at use cases and finish with Q&A as always. And to get going, let's just have a quick look at what thermal runaway looks like. I'm going to show you a quick video of two 4680 cells. Those are the ones that are used in the Tesla Model Y. In the actual car, they're about 800. Here it's 2. They're fully charged. I hope the video works and you can see that well. You can certainly see a lot of energy being released, a lot of gas being released, and a lot of mass being ejected from the cell. Those 3 properties will be important in a second. I think it's pretty self-explanatory why it's nice to prevent this from happening, but there are 3 objective good reasons for that. The first one we already mentioned, it's certification. If you want to release a car, you need to go through homologation. If your car isn't safe according to the standards, you can't sell your car. The second is ethical. If you see the picture here of a screen grab from a Air China flight where a battery caught fire in the overhead compartment, I wouldn't want to be the battery designer or owner of the company that built that battery when that happened. Thankfully, everything was okay, but could have gone much worse. And the last one is a big one because it's commercial. Like if we release a product into the market, it's our responsibility to make sure it's safe. So even when there are no super strict propagation containment requirements like an automotive, dealing with a product recall or an insurance claim can be very, very costly. So it makes sense for everyone who builds batteries to factor in safety into their development. And the best time to do that is early on when you still have a lot of wiggle room. This is why we developed DATRC, long acronym. You don't need to know what it stands for. What it does is it allows us to fingerprint cell safety behavior. We can essentially quantify the safety of a cell with a single measurement to understand how it like behaves objectively. We measure the total energy that we discussed earlier. So how much energy is actually released by the fire, by the explosion. We determine where that energy is released. Is it ejected from the cell or does it stay behind in the cell and leads to a heat up of the cell? We determine how much gas is generated by the reaction, the rate at which it's reacted, how fast the cell reacts, mass loss, and a bunch of other properties that I don't have time to get into. I brought a quick example here. This is from cell selection. We have 3 manufacturers of roughly the same cell according to the data sheet. It's a 5 amp hour 2170 cell. 3 manufacturers, China, Japan, Korea, not in that order. And we triggered the runaway in our method. We're going to look at the energy as an example, and we can see that the total energy released by the fire, by the explosion, is roughly the same for all 3 cells. But when we look at how it is released and where it is released, we can look at the cell body energy fraction, we call it. So that's the energy that's released in the cell itself and leads to a heat up of the cell and a heat up of adjacent cells. When we look at that data in detail on the right, we see that the cell from manufacturer 3 releases about 13-ish kilojoules of energy. The cell from manufacturer 1 releases about 20 kilojoules, so roughly 30% more. That means if you have an application where cell-to-cell propagation is a huge issue, small cell spacings, like high requirements on weight, it might make sense to go with cell 3 because you'll have an easier life designing a propagation-safe design compared to cell 1. In general, this information is useful everywhere where we compare cells to one another, like in cell selection, or where we need to understand cells in a lot of detail. So we touched upon cell selection. We actually also do a lot of work with cell developers, where we track if the cell safety changes through generations of a cell. You go, like Federica mentioned, through scale up, does something change to your safety behavior as you produce more cells? It's also very, very helpful for edge case behavior. A common one is lithium plating. A lot of people at some point ask, holy shit, what happens if my cell plates? Does that change my safety behavior? We can run our test on pristine cells, on plated cells, compare the behavior, and then we know where to look and if we need to change something in the design or not, so be active essentially. Speaking of design, that's the last big application field. We have really nice quantitative data on the thermal behavior of the cell and the gas release. So we can just do proper design using empirical data, like, for example, sizing thermal management systems. Super quick summary. I'm looking forward to your questions. Thank you.
Thank you very much, Dominic. So if there are questions from the audience, please put them in the chat, raise your hand, use the chance to talk about this with Dominic. I have the first one, actually. Maybe it's a little bit like picking words, but one of the headlines was lithium batteries for bicycles are the fastest growing fire risk, which is not equal to a high fire risk. Could you maybe comment, like maybe also compared? I mean, we always have dangers, like cars can burn as well. Could you maybe give us a crude overview of how dangerous are batteries right now? Like looking overall, not on the specific cases where they went crazy, but the occurrence of these accidents.
Sort of the failure frequency. I can't give you like exact numbers. I'm not an expert on macro battery recalls. I can tell you that Sony recalled laptops because 1 in every 200,000 laptops exhibited different thermal behavior than normal, which means that 199,000 and something laptops were okay and still had to be recalled. Anker just recalled products. Volvo just recalled cars. Volkswagen just recalled cars. Like, it's a very, very common occurrence, even though I can't give you exact numbers. It happens like all the time.
All right, thanks for that perspective. And Simon, you have a question.
Yes. Going back to when I worked at RWTH and had at eLab, we also had a battery testing facility. And the critical question was always, how many amp hours do you get put in the chamber there? And that's the critical question to you, Dominic. So how much amp hours can we do until the doors pop open?
Really good question. So we can do about 100 amp hours if we want to include gas analysis. We can do about 300 amp hours without gas analysis, because the gas analysis equipment wouldn't survive the extra amp hours.
Okay, good. But that's so for all the startups here who want to test, now you know how big your cell can be.